got a tenure track position at the University of Georgia.
Yeah.
So over there, he got tenured. And he had his first PhD student, Changsheng Chen, graduated over there. And some of you may know him. Dr. Chen has been working in this college in Bob's group for a long time. And recently, he moved to NOAA. So they found his expertise. They grabbed him. And in 2001, Dr. Chen moved to UMass, to Dartmouth, to be a professor over there. And over there, he expanded the group. And also, he expanded his model to cover large areas. And now he's endowed chair professor over there with guaranteed funding and a great honor. So I just learned this is the second time Dr. Chen is in St. Petersburg. The first time was many years ago when our new building was not put in use yet. Yeah. So there's quite some change in St. Pete downtown, but unfortunately
that's 1996, something like this.
Oh, maybe before that.
Yeah.
But he has not
before that.
To see our new St. Pete.
Yeah.
So we'll see if we still have some time after this. You may notice the screen now is a little bit smaller. Okay? So we spent 20 minutes, couldn't figure out how to make this work. So this is my ultimate solution, a $100 projector. So it works good. But for that, we don't have a chairs here. Okay. So today, Dr. Chen is going to talk about his global, large scale, regional scale, small scale model and the applications. Let's welcome Dr. Chen.
Okay, thank you. It's very happy to come here. The first impression is get a warm weather. Yeah. Right? Also, I can see my former boss. Yeah. So today's my topic is to talk about downscaling simulation for ocean response to climate change. So it might introduce to you about the global basin coastal nesting and the FVCOM system. So the outline, I give a short outline here. So the first thing is why we need to do the downscaling, right? So, what the critical need for downscaling the climate change model. But we have a lot of Earth system model later is introduced to you. US has been developing a lot of Earth system model. Now so all the world scientists use this model. Okay, but the question come out, should we change something, improve this kind of Earth system model? That's the quick. Second, I talk about introduce, because I don't talk about science here today, okay? Because I see that people come here with different kind of, physical oceanographer, biology, talk too much modeling. I worry about people confused. As I give an example, tell you about global regional coastal estuary FVCOM system. So why we need to develop a model like a FVCOM for global ocean, okay? Why? So what the difference for this model is? Then I give you some example. Some science example, scientific example, some application example. You can use the earthquake, the model. You can go to ocean, if an airplane lost, you can find the airplane. And a lot of applications show you some example, give it to you. So then later I talk about, reasonable process multi-scaling Earth system model. We have been developing a new Earth system model right now, resolution about 100 meters in the whole global. So I tell you, this is the picture. This picture is about satellite data. We had a satellite expertise here. I download the satellite data. I do the annual change rate for global surface temperature. So this is the change rate per year. I use data for 1982 to 2015. Thus, you found our region. You found our region on the Pacific Ocean. You can see that our California coast is warming significantly. So in the North Atlantic Ocean, you can see our Gulf Stream areas is warming. Even the warming, the degrees every year is less than 1.1 degree, but still it's warming. The tendency is clearly. But the question here is not the warming every place. It's warming is a function of space, right? You can see we got a warming here, sorry. We get a warming here. No, we get a cooling here, right? So that's why you can see the origin is warming here, but it's not every place. So you look about the ST, then you look about ice. The global warming here, you look about the Arctic Ocean, that's the Arctic Ocean ice. You look at climatology averaging, this is 1978, this one. You can see the summertime ice look like this. The 2007, ice quickly was melted. You only had this part of ice. So then after that happened, ANSWER called a meeting. People go to Washington, D.C. So we say, oh, that's what happened 2007. What happened next year? So after next year, they come back. They come back. So then in 2012, in September, they get another ones come out. So when you look at the trend, the ice coverage area, you can see they get decreased trend for the year, but quickly, this couple of years, variability is bigger. Not look at the down here, but question is here, is you get a change very significantly recent year. So we talk about climate warming, but the questions come here, it's not just generally is warming, is ice lost, but they also have a big change annually. So then you look about Southern Ocean. Oh, sorry. I look at Southern Ocean. You look about this one, you say, okay. You look about ice coverage. That is, you look a couple years. That's 1979. That's 2008, 2015. You can see the ice, more and more ice in the ocean. So that's why you say, oh, the Arctic Ocean ice melting, while the Southern Ocean, Antarctica get more. The reason because ice shift, a lot of ice from land move to the ocean. A lot of ice on the land, they shift into the ocean. So then you look at the increase, you look about a change of ice coverage, you can see this ice will get more and more gradual increase. Also, variability becomes bigger and bigger in recent years. So we don't know. Is climate change make us warming? But one thing that's in fact is variability is bigger. So then what will happen? You look about PCO2. I'm working on the global ecosystem model. Okay, so for the England people, so then you got PCO2 global. You can see our PCO2 annually change rate is all increase, but this is not satellite data. This is survey data. Okay, that's why you can see here's no any data, but you can see larger survey down here. You can see annual increase also increase in the Pacific Ocean, Atlantic Ocean. CO2, people talk about climate change a lot. So biology people think about this one ocean, ocean. This problem come out, CO2 come out, ocean acidification changes. The pH has been decreasing. That's the whole thing we talk about. It's the whole thing. I'm not a biologist. I show you what happened. So then you see the pH. You ready as the pH come out. You see the pH? Oh. No. Why didn't you show the picture? Okay. Okay. You see the pH here, global pH value. You see the pH has dropped in a lot of the regions here. That's the annual rate. But this is all that happened in the pH, okay, ocean, the pH drop a lot. Then you look at Arctic Ocean. The big climate change issue is the Arctic. I have been studying Arctic for many years. So you look at Arctic Ocean circulation, you look about here. This line here, this is up 50-meter circulation pattern. You see the dry circulation like this way. So then you see the whole Northland water getting in, then the Arctic Ocean get out. That's all the deep ocean circulation look like this way. But the recent year, things has been changes. So in this region, water has become fresher and fresher. This is a salinity picture here, 2003, 2004, 2005 to 8, 2009 to 10. You can see the region here. This region, we get the water become fresher. Then question come up. We had a lot of discussion with this. When the circulation becomes weak, then all the fresh water come out. If we go out for Atlantic Ocean, what's really happened? Because now the Arctic Ocean becomes the region accumulating the fresh water. There are a lot of theory talk about the ocean. I don't want to talk more, but the question come out is climate change changing Arctic Ocean. when we wait what happened for Arctic Ocean for next 10 years, so what could happen for North Atlantic Ocean? So then you look about here, sea level rise. A lot of people talk about sea level rise. We spend a lot of time to do the sea level rise. This is annual change rate for mean sea level. This is the rate we use the data come from satellite data. You can see this one, mean sea level rise, 1993 to 2015. You can see we get a sea level rise, larger region, but it also is a function of space. So why we need to worry about sea level rise? We say, oh, sea level rise come here, the storm will come here, we get a much region be flood. But what's the cause of flood? We has been recently, NOAA had the answer from us. We do a lot of research. You look about storm surge. We talk about it. We talk about a storm surge. We get a tide elevation when you get a high tide. When the storm come here, you get a storm surge. That's the total sea level we worry about. So then we said, okay, if the total sea level high, we get flooding. But one significant physical process we missed all the model right now is the wave runoff. What means wave runoff? When you come here, you watch the beach, right? You see the big wave come, right? So flooding the whole area, not the total sea level. A lot of the time. I can show the one movie to you to give you evidence. That's what happened in China in 2015, okay, August 7th. You can see this picture here. You can see the wave runoff cause the whole region flooding, but total sea level is below the seawall. So they spend a lot of money to build the infrastructure, right? But however, the city will be flooded completely just by the wave runoff. So what happened when the sea level rise? What is the wave runoff could be happen? That's the question we need to address. So the same things happen. Not that that's the only China case in our coast. That's the Massachusetts coast. Massachusetts coast. In 2015, January, we get a big storm come here. They run off, get the whole city was flood. But we are in the north. That happened in January. So for whole region after one day, freezing. Whole city freezing. Nobody can walk. You can ski over there, but not able to walk. So then, what you can do for this? For sea level rise, today I don't talk about storm surge model, but I can show you what the research has been done recently, results to you. We found we had a whole high resolution model, do the whole simulation of the sea level rise. We found, this is generally the 15 case, that's the wave runoff for transport. If you get 0.5 meter sea level rise, you can increase 18%. If you have 1 meter sea level rise, you can increase 36%. What if happen in the future? In the future of the war, we get more storm, most damages the total sea level is the wave runoff. Right? So we had to have a new thinking to the storm surge model. So for all this one here, what do we need? We need the model can resolve the global ocean for ice melting. The go to the estuary can resolve the tidal marsh. Also the storm surge get a coastal flooding. The question is, can we do that? Right? So that's the physical oceanographer. Just a question said multi-scaling. Ocean circulation has a multi-scaling. We talk about global ocean, three basin water exchanges. That's global. We do the basin, we get a Gulf Stream, we get a subtropical dry circulation. It's a basin scale. When we do the coastal, we get coastal from the kilometer resolution 10 kilometers. So then we go to the region there, have a cooling, we get a convection, we get an internal wave. But internal wave scale is 1 meter. Can we do the global ocean climate, then also can do the internal wave, right? How we do that? Then what is the challenge for us? The challenge for us, regular observation 4-dimensional networking. So we don't have enough observation, right? So we're not able to resolve the multi-scale process by observation. You know, here we put a 1, here we put a 1, we don't resolve it. But most things, we regular systematic understanding impact climate change to coastal ocean. Most of the climate change people, they're working on Ansel, right? El Nino, right? So then some people working right now we're working in the Arctic Ocean, but we don't really know, you know, what happened. The one senator come to my office asked me the question, Arctic Ocean changes, what happened for Massachusetts? Tell me how long time to wait. So we people say, well, we don't know anything. So I don't know either. I said 2 years. I think because the water come from Arctic Ocean, move to Massachusetts, they could take 2 years, right? Oh, he said, oh, you're smart, but I just by guessing. You know, so then a question comes, you know, so we need to have a multi-scale interaction. We don't know. So we need a result at the multi-scale, at the mass coupling. You look at all the Earth system model, ocean and the atmosphere same scale, right? But then you go to Texas shelf, you do the 2 times wind measurement, you find the correlation scale for wind is 100, 200 kilometers. Then you look at circulation, the correlation scale 10 kilometers. How you coupling the 100 kilometer system with the 10 kilometer system together at same grade, right? So that's reason this reason cause like a multi-scale without atmosphere ocean interaction. Ocean had a multi-scale, but also air sea interaction is multi-scale. So without a multi-scale, that's come out the issue. You get a global ocean, you get a coast, you get irregular geometry, you get a tidal creek, right? So then you get a short break. So then a quick issue is mass conservation. So you get the whole thing together. How you guarantee the mass conservation, right? How you guarantee one to link another, not to lose the energy? So then we talk about Earth system model. Come back. All the Earth system model right now is structured gray. That's rectangular gray. Okay, but you don't understand when we had a question come out. No any model in the world can be resolved actually surface gravity wave. My model, no anybody model, all models are wrong, okay, including my one. Okay? The reason because look at the shallow water. When you get a shallow water here, we had a surface gravity wave, very simple surface gravity wave model. It's a non-dispersive wave. But when you do the numerical model, you know, doing the wave calculation, your wave speed depends on your model resolution. That means when you do the model, the wave is propagation lose the energy because numerical resolution. But if your resolution go to 0, delta x go to 0, they come to a true solution. But no one can get a 0. If you go to 0, you don't need the numerical model anymore, right? But the solution come out, you have a 2 nesting grade, regional, global, global, regional. You have to have a boundary nesting bound model. You have 2 different kind of grade. What happened? You have a 2-way propagation with a different speed, go to boundary. The energy can be accumulation at the boundary. So you're not able to run the model for 100 years. You can run for a couple of days, right? Can write a good paper, but not a good for system. So then we proposed the idea. We said, no, we should have an unstructured grade. What happened unstructured grade? That means triangle. You know, when you go to elementary, middle school, what a teacher tell you, 2 lines determine, 2 points determine the 1 line. 3 points determine the area. That's the minimum number you can determine the area, right? That's why triangle is the most simplest way get the area fitting. That's why I use a triangle here. You can see here, I have a 2 domain. I want to nesting together, but my boundary is a common boundary. Make a triangle, 2 boundaries exactly the same. So my wave propagation is still not correct. At least they get the same speed. They not have energy accumulation over here. So then what happened, if I say that this had a small island here, I want to start an internal wave. I need to include internal wave module. I can make a high resolution here to do the internal wave with different dynamics. So the unstructured grid can be making you everything is simple, everything flexible. Okay, I have a colleague. We write an OR proposal a long time ago. I'm not working OR anymore. Okay, so then I make the grid, use the half hour, make a triangle grid. He used the Ron's model. Ron's model is a good model, right? Ron's model, he take about 3 days. Then he still, 3 days, he still not can resolve the tidal creek. He tried very hard to get the creek there. It's really hard. My one, I just put a pointer here. Oh, 10 camera resolution is good like this way. That's why to make it easy. That's the unstructured grid. That's why if you do the global nesting, you have to use unstructured grid. You have to use this model, can make the whole system network. Basically, that's what we're doing. We had a global ocean model. That's a 2 kilometer resolution, not a 5, okay, 2 kilometer resolution. We had an Arctic Ocean, 500 meter resolution Arctic Ocean model. We had a mass coast model, 500 meter. So we get a mass bay model, 15 meter. So we get a estuary model, 10 meter. Whole system linked together, round, same time. Okay? So then, this model already put a forecast. This is the, okay. This was already forecast. Okay, what? This is forecast, this is forecast, this is forecast. This is all forecast. So now you go to our Massachusetts, right? You go every place, the 10 meter, the stone region, you can CT, we do the every day, 3 days of forecast, include the global to the coast. So based on the idea, we build a northeast forecast system. So system we build, global ocean model, nesting model here. Run the global ocean model 3-day forecast only use 15 minutes. But use this one, use 3 hours. Then use this one, probably take about 6 hours. Then you have a full inundation model, do the storm surge prediction. Fully wave and current coupling. So I show you what the grid they are. Look like an inundation model. That's the Boston Harbor. You see here, that's the Logan Airport. That's the grid you have a cover region. So that's the region you see here. Every 10 minutes we resolve. So we can make a prediction, see how the sea level rise. We have a global model run for fun, right? But then we provide a state service is like this resolution. I can give you a couple examples for global ocean model. You'll probably see you showed a nice picture, but you didn't show the circulation. So that's the circulation, global ocean model. I couldn't put every point. This is the particle. I put every place the particle. I like a particle moving. I want to see how the global ocean move like. So this is you see, this is Taiwan. That's Japan. That's a Crucial. That's a lot of 80 circulation there. You can zoom in there. You can see the more circulation. Whole circulation. You can zoom in here. That's a Crucial. And moving here, very detailed. So then, okay, this was on the forecast. So then you go to our region, North Atlantic Ocean. You can see the Gulf Stream, simulation Gulf Stream. So then you can see the circulation Gulf Stream there. You can see the, this water come from Labrador Sea, Arctic Ocean come down here, right? So you look at that region we studied the Georgia Bank. You can see very detailed. So then you go to Arctic Ocean. You can see the Arctic Ocean. You can see the circulation very detailed. You can see the circulation getting in here. They straight coastal jet current here. So then you separate it, the whole circulation. You see the North Atlantic water getting in, Arctic Ocean water get out. You all resolve, right? So then you see the Southern Ocean. You see the second polar circulation over here. You can see the whole coastal current, all resolve in the Southern Ocean there. So then you see the ice. You can see the ice. This is a comparison for ice. This is observation. This is a model. This is satellite observation. Okay, so you can see this why we simulated most of 38 years without a data simulation. You don't need a data simulation to get ice corrected. Okay, you can see the simulation ice. So you look at ice, you say, no, I'm not very interested. You look like a similar, but then I show you what a high resolution model is. This one is ice drifting. Very funny story, people have, like a French scientist put an observation station in here. Now, then their station keeping moving year by year. So their observation station look like a drifter. They keep moving here because ice drifting. Here is no yellow one, but the blue one is the model, red one is the observation. With simulation, it's 38 years. We get all data come out, see how good it is. So then you see, I'll give you an example. Multi-scale. Okay, when you go to small region, you want to see the ice. You can see how the ice was breaking, converging. You can see the whole eddy, called an eddy. Ice, when ice form, they can cause like an eddy and the current interaction eddies. Okay, you can see over here. That's the Alaska coast. You can see how ice was formed. We can study very high resolution ice, how ice formation in the Arctic Ocean. So I show the people say, don't show us anymore. You make people nervous. So we talk about a 16 kilometer resolution model right now. You tell me about a 500 meter resolution, right? Get out of the door. Okay. But that's what we'll be doing, okay? So now I show you massive scale eddy. You see that's a lot coastal here. You see the circulation. You see the old eddy can be simulation the region in the coast between the ice and the water. Okay, so you see the whole ice there. You can all simulation. That's become an Asia ice model. That's for Arctic Ocean. So that's the simulation you get. So you see comparison with the observation. That's the comparison. We got ice intention, then ice anomaly. You see that we get also big variability in recent year, but not a very exact match. But it look like good. So then, when you do the ice model, you very easy get the ice correctly for extension, but ice thickness is really tough. Observation tough, then also model is tough. So we compare with the ice thickness data. Look about this picture. Tell you something. This is U.S. coast. That's the Russia coast. Russia has spent a lot of time to do the ice study. U.S. has little. So they get all data come from Russia. We get all data come from Russia. Russia also put a 51 station, long-term station here, around the measure with ice thickness. So we compare the all data. That's the comparison result. When you get a global ocean model, next step, regional model. That's our regional model. I just showed some movie for government region. You see the include tides. Okay, circulation here, moving. That's the color is the temperature. Okay, so you can see when you regional model, you can zone in the Mass Bay, Boston Harbor. You see the very high resolution here. Then go in here, you can see this is 10 meter resolution here. Now we get a whole software developed. You go there, you make a list. Coupling. We try to make everything simple. You see here the flooding going here, get in, get out. So then you do the estuary. When you do the estuary, so this is a river. So that is a wetland. That's a salinity. You can see the water getting in here. They're all flooding by water in the tidal creek. Then go down, the dry. It's also, this is the Merrimack River. It's all change we can resolve. That's resolution is the 15 meter resolution. 15 meter resolution. So then we do the internal way. Now we get a lot of internal way on the Stone Wagon Bank of Massachusetts here. A big stone in the summertime get a lot bigger internal way. So then you can see, that's the internal way, here. You see the internal way? They're beautiful here. They can simulate internal way. Period is only 5 minutes. 5 minutes period. The vertical solid hung, like this one is a 60 meter, depression. The propagation speed is really fast. So then you can get a global nesting go to region. You can do global. You can do the small scale. So that's not just a plan. That's what has been happened. So we make the northeast forecast system. That's the forecast system in the forecast. So you can see that, let's repeat some. You can go to our website. You can look at all the comparison observation. You can zone in, zone out, look at global, look at regional, look at estuary, look at inundation. Even inundation map we provided. Okay? That's why you get a station here, you can go to website, you can go here. So now I tell you, when we the global ocean model, before we the US scientists, right? Now we become the scientists for war. So when Japan happened an earthquake, like a March, okay, March 11, 2011, today remember, earthquake, right? There was a big tsunami. The Japan government called us, asked us to help do the simulation, see what's really happening for nuclear plant. They don't care about the tsunami, they care the nuclear plant. So Bob Beasley, my former advisor, and I write a letter to NSF, ask NSF give us money to do the assessment. NSF said, no, I don't want to intrude in front of you guys. The reason because it's already happened. But then we told NSF, Japan agreed, release their 5-meter resolution persimetry data to US. Do you want to make a deal? NSF said, go ahead. They give us the money. Then I look about earthquake, okay? Then look about, I give you some refresh memory. This is the nuclear plant. You look at the 4 station. Reaction 1, 2, 3, 4. You see the facility supporting room over here. You look about here. Then you look about here. What's happened? So this is reaction plan. You know, machine reactor was here. Why the back side was damaged? Why not the front side? Right? So that's really interesting. Why the tsunami come here? Why the front side not damaged? Why the back side was damaged? Right? Do you know the answer? You know, you have a big wave come here. You should be, the front side should be damaged more heavily. Right? Right? What happened? Why the back side get damaged, not the front side? Later I told you the story. What the story is. So then you look about a nuclear release. Okay, you can CS 137, 30 years half lifetime. You look about this Wusuo scientist did. You see that they hold, nuclear material, radiated material come out. You see the huge. Now compare the one, the Russia one, like this. Okay, but the Japan one is so huge. I don't want to talk about too much about this. I just want to show it because time's limit. I don't want to take you a lot of time. Okay, already had a 10. That's the assimilation tsunami, 5-meter resolution model. Tsunami, what really happened? You see here, when the wave tsunami touched the northern coast, southern coast first, so the energy was reflected back. When it reflected back, so all the energy reflected back, okay, the region, so then all convert to this region. So then all the region over there, big tsunami happen for the flooding here. Then you look about, that's what happened. You see the flooding, then you go down, the second one can come out again. It's all the mathematical model simulation. So then you look about, with a nuclear plant. That's what happened. Now, all the nuclear plant designing use this one is called this uses protection of wave, right? They only protection 5-meter high wave, but this tsunami 30 meter higher. What really happened? You find the tsunami come here. You two dam. The dam not stop the wave go around with the dam. So then the wave get into the from here, come here, from here, come here. They all come from back. The water come from back side go to ocean. So that's the reason you get a flooding for back side, not in the front side, because there's two dams. Okay, so then you see how the nuclear materials open. You have to have a model 5-meter resolution. This is the nuclear materials can open. This is how everything comes from plant. If you use the regional model, they go every place. That's the people worry about. U.S. has been had a water already come to U.S. But you use the real model, you find all the materials stay the Japan coast. Recently, they go to measurement in the bottom sediment. All the sediment concentration is very high. Not much in our region, but most stay on the Japan coast. But you need to have a model without a power plant. I'll give you another example. Airplane. You still remember this? French Air 447. That's a crash when from Basel they go to Paris. The June 4th they lost here. They searched for 2 years. They cannot find the airplane. Picture I can show you. That's what the picture you get. So this is the last node position. The circle mean you get ground speed, no airplane speed. You times the 5 meters. That's the maximum place you can go. Right? That means the airplane is definitely inside this region. But then the red one here is the body they found, 58. That's red. The white one is the debris. They get a 218 debris. They search after things happen. U.S. and the veto, a lot of people go to measure. We're going to survey here. That's a survey area. Survey area. The survey for 1 time, 2 times, fail. Then they call us together. Okay, so it's here. So then what happened? They call us together, use our model to the tracking. So we said, no, we have to change the way to tracking. We have to have a resolution converging. Like make sure the body can really go to your model tracking. Okay, I don't talk a lot of technology. I talk about things here. But then what I find here, so I use the high technology of model resolution. I use the body, reverse body. I found the body should be here. Right? That's a 4th search, 2nd year. So then what happened? They found the airplane there. They found the airplane here. Right? We tell people there, because we do the search 1, fair, search 2, fair, search 3, fair, the 4th search. So we tell them, should be go to search here. Right? Then they go to search there, we find the airplane. Okay? Now Wusaw get a lot of money, I think a couple $1 million. They just contract us. But they don't allow me to attend. The reason because when the 2nd search fair, 3rd search fair, I represent who you get a meeting out of Paris. I told people, I said, what you do is stupid. You couldn't do this way. You never find an airplane. How you use the high count 10 camera resolution model to prediction where the particle go, right? Whole particle stayed probably less than 10 kilometers. But then the guy get mad at me, take me out in the office, right? So then my budget come from is for supplies on the Hui budget, okay? But we find the airplane, that's make us happy. Okay, now what are we working on? Okay, I just tell you what we're working on. So we has been developed a new assist model. You see, this is NCAR-SAM. You people know NCAR-SAM, community assist model. You get a atmosphere, CAM5, you get a land model, you get an ice model, ocean model is a POP. They use the same scale coupling. Now what are we working on? We try to replace a global FVCOM to coupler, replace this one. Not replace, just an additional one. So key issue is to resolve multi-scale. Why we need to do that? I should just show you. You look about FVCOM results, look at NCAR-SAM, very similar. Right? Just we get a high resolution look at, but then you go to coast, then you get a difference. That's the NCAR-SAM model prediction, the temperature and the coast. You see, no Gulf Stream. Right? No level of seawater come down. The boundary is Gulf Stream. This here is the boundary, temperature. They result a little bit of Gulf Stream, but too weak. This our model show the Gulf Stream. We get a level of seawater come down, result the whole coast. Once result coast, one or result coast. So we want to keep everything NCAR do, but only you get additional unstructured grid model without a downscaling. Okay, I just want to finish. So now I organize a team. The US is not able to do that because we don't have a supercomputer. No one provides the free computer time. I go to this region called China Tianhe-2 supercomputer. That's the fastest machine in the world right now. It's called Sun Yat-sen University, That's a university computer. Okay, that's the whole building is a computer. There's a whole building. So this is a computer like a trim. They get a 7 is big like this. So then when they turn on, look like a color, 2 million nodes. Each node has 24 CPU. Okay, so I make it there. They let me free to use, okay? But then they want to use my model testing their computer because nobody uses the computer, right? So Chinese don't use, US people happen to use, right? So once you use, we transfer data back here. So this is me, the 3 engineers. They signed for me for free, working with me, completely free. I have no money to pay them, okay? So then last picture I show you. Then we're working for UK people. We develop a system ecosystem model. Before you get an ecosystem model, here you get a whole ocean atmosphere component, you get an ocean component, you also have a geochemical component. This model has been running in the UK, now we move to the US, we're testing right now. So we were testing in the Mass Bay coast. After testing, we apply for global. Okay, talk too much, thank you very much.